So in the next few lectures, we're going to try to conclude our discussion of integrals. So let's recall the first part of the fundamental theorem of calculus. If I have a continuous function on some interval, so I have little f defined on the interval CD, and it's continuous, I can define capital F on CD, and capital F is given by integrating little f, right? So capital F is the integral from c to x of f of t dt. If I define capital F this way, then it's an antiderivative of little f. Okay? So capital F prime is just little f. That was fundamental theorem of calculus part 1, and we gave a proof for it. And we explained kind of how to interpret it by areas and differences of areas, and the reason for this is because of one particular tall rectangle. So if you want to see the proof of that, go back to the fundamental theorem of calculus lecture. So let's see a few examples of how we can use this. So capital F is the integral from 1 to x of sine of e to the t dt, and we want to know capital F prime, right? So terrible thing to do would be to try to integrate this, so find an antiderivative, plug x in, and then take the derivative. So the capital F is defined by integrating another function. So here, this is going to be my little f, and so the derivative, capital F prime of x, is going to be little f. So I'm going to have sine e to the x. Okay, so here, it doesn't matter what I call my variable here as long as it's the same thing on both sides. T is a dummy variable, so I want to use x on both sides here. It doesn't quite matter. If I use t on both sides, it's okay, but here t is a dummy variable, x is my real variable, so x is a good idea to have it in my answer. Right, so I just, capital F is the integral of little f, so the derivative of capital F is just little f. Right. Again, integral from 3 to x, e to the e to the t, f prime is e to the x. Right. So if I asked you to actually do this integral, it would be very difficult. So here, one slightly tricky one, integral from x to 0. So what I'd like to do is, well, using my properties of integrals, I get an integral from 0 to x, sine of t squared dt. And now I can take the derivative of this, so minus sign is going to stay minus sign, and then by exactly the same thing we've been doing in the previous problems, I'm going to get sine of x squared. Right, so they're my derivatives. So let's look at some applications of the fundamental theorem of calculus. So let's assume that f is continuous in CD and have some other function phi from AB mapping into CD, and that phi is differentiable. So I'm going to define capital F on CD by integrating little f, just like before. So by the fundamental theorem of calculus, capital F prime is little f, exactly like on the previous page. I'm going to define capital G to be the integral from C to phi of x. Okay? And notice that G and F look very similar. The only difference is that here I have an x and here I have a phi of x. So G of x is just the composition of capital F with phi. So I take capital F, and instead of putting an x, I put in phi of x. That's the composition. So by the chain rule, the derivative of capital G is f prime of phi times phi prime. And I know capital F prime is little f, so I get this. So, so here's the kind of end result. If I have integral from a constant to a function of some function, then the derivative is I take this phi, plug it in here, okay, just like in fundamental theorem, but now by chain rule I have this additional factor. So I don't just take phi and plug it in, okay, so I do that, I take phi and plug it in here into my function, but I don't just do that, I also have this phi prime because of chain rule. So for an example, let's take this capital G. It's an integral from 1 to e to the x, 1 over t dt. So g prime is going to be, well, I'm going to take e to the x, plug it in, and I'm going to multiply by the derivative. So here, my little phi is e to the x, the derivative of that is e to the x, so I get 1. Right, so capital G prime is 1. Turns out that g of x is just x plus a constant. Plug in a constant, right? Plug in x equals 0, you find the constant equals 0. Right? G of x is just x. Right? So I can plug in 0 on both sides. Plug in 0, get integral from 1 to 1, that's 0 equals 0 plus c, so c is 0, and g of x is just x. Right? So related to that, let's define this other function. Okay, so we can call it capital L. Capital L is going to be defined on the domain from 0 to infinity, and capital L of x is the integral from 1 to x of 1 over t dt. right? So note that L of 1 is 0, because if I integrate from 1 to 1, I get integral from anywhere to the same place is 0. Right? Now if I fix any positive number y, and I do this composition, derivative, so here y is a constant, and x is a variable, I take the derivative, and by chain rule I get this. Right? So capital L prime is little, so capital L prime is 1 over x, just because of fundamental theorem of calculus. Right? So capital L prime of xy is 1 over xy times xy prime. Well, here y we're treating as a constant, x is the variable, so xy prime is just y, so we get 1 over x, and that's the same as L prime of x. So the derivative of L of xy equals the derivative of x. Okay? So by the mean value theorem, since these two functions, L of xy and L of x, have the same derivative, one of them is a constant plus the other. So I input x equals 1, and I get L of 1 times y, which is just L of y, equals L of 1, which we said is 0, plus c. And so I get c equals L of y. And so I can plug in c equals L of y up here and get L of xy equals L of x plus L of y. Now, for any real number, I can take the derivative of L of x to the r, okay? And by chain rule, I get L prime of x to the r times the derivative of x to the r. Okay, so L prime is 1 over x, so I get L prime of x to the r is 1 over x to the r. Derivative of x to the r is rx to the r minus 1, so I cancel here, and I get r over x. Okay? And so this is r times the derivative of L. So L of x to the r has derivative equal to r times the derivative of L. Right? So isolate here. So if I take the derivative of L of x to the r, and I take r times L, and I take the derivative of that, I get the same values. Okay, they're both equal to r over x. We just proved that. So these two functions have the same derivative. That means one of them is equal to the other one plus a constant, again by the mean value theorem. Okay. I have two functions defined on an interval that have the same derivative on that interval, then one of them is the other one plus a constant, and we proved that in the mean value theorem lecture. So if I input x equals 1, here I get L of 1, which is 0, here I get L of 1, which is 0, plus c, so c is 0, and I get L of x to the r equals r L of x. So notice that L prime of x equals 1 over x, which is positive, so that means that L is strictly increasing. Okay? If it's strictly increasing, it means it has an inverse function defined on whatever the range of L is. Right? So for every output of L, there's an inverse. Right? So I don't know what the range of L is yet, so I actually do know, but we're not going to say. Okay? And by the derivatives of inverses, right? So we proved before, if I have a function in the inverse function, the derivative of the inverse function at x is 1 over the derivative of the original function evaluated at e of x. Here, I know L prime of something is just 1 over that something, right? So L prime of e of x is 1 over e to the x, which is e to the x. So this e of x, right? So e prime of x equals e of x. Right, so we prove that. Okay, so the inverse function has this important property. Can also prove that L of 4 is the integral from 1 to 4 of 1 over t. So let's say, so L of 4 is the integral from 1 to 4 of this function 1 over t. And if I just do a lower Riemann sum here with this partition, I get, for my sum, I get 1/2 times 1 plus 1/3 times 1 plus 1/4 times 1, which is greater than 1. So that means that 1 is in the range of L. L is 0 at 1, and at 4 it's greater than 1, so somewhere in between L is equal to 1. So let's let alpha be the number such that L of alpha equals 1. Here I'm using the fact that L is continuous. Not only is L continuous, but it's differentiable. Right? So L of 1 is 0, and L of 4 is greater than 1. So by the intermediate value theorem, there exists a number alpha such that L of alpha equals 1. And now for any real number, r, L of alpha to the r equals r L of alpha. Right? So we proved this property of the function L on 2 pages ago. Right? And now I know alpha was chosen so that L of alpha equals 1, so r times L of alpha is just r times 1, which is r. So the inverse function, e of r, is just alpha to the r. So L of alpha to the r is r, so the inverse function goes the other way. E of r is alpha to the r. So notice that we were able to say a lot about L and E without ever really saying what they are. Right? So I never really said anything specific about the functions L and E, but I was able to deduce a lot of properties of L and E using mean value theorem and mean value theorem, intermediate value theorem, and fundamental theorem calculus. So using these things, I was able to prove a lot about L and E without ever having a real concrete definition of them. So let's continue. Let's talk about U substitution. So let's say I have a function defined on CD, mapping into R, and a function phi going from A, B to CD, and it's differentiable. And so we know about U substitution. U substitution basically tells us this. So oftentimes we do U substitution with indefinite integrals, but we don't have indefinite integrals here. Right? I forgot to say that the endpoints should go to the endpoints. Phi of A should be C and phi of B should be D. Then the integral of f of phi of t times phi prime of t dt is equal to the integral of just of f. Right? The proof is define capital F and capital G in the following ways. So capital F is integral from c to phi of x, f of u du. So if you go back to the first or second page of this lecture, I know capital F prime has this derivative. So it's a combination of fundamental theorem of calculus. Fundamental theorem of calculus tells me that if I want to take the derivative, I take phi of x, plug it in here, and then multiply by phi prime. Okay. So here's capital G is the integral from a to x of f of phi of t, phi prime of t dt. So if I want to take the derivative of g, I just take x and plug it in here. So capital F prime is this, capital G prime is the same thing. So capital F, capital G have the same derivative on their domain, which is AB. Two functions have the same derivative by mean value theorem. One of them is the other one plus a constant. Okay. But f of A is 0 because it's the integral from c to phi of A, but phi of A is equal to c. Okay. So it's the integral from c to c, and that's 0. And g of A is the integral from A to A, which is also 0. So the functions are, so f of x is just g of x plus a constant, but they're equal at this point, so the constant here has to be 0. Okay? So f of x equals g of x, and in particular, if I plug in f of b equals g of b, and if you recall that phi of b equals d, right? So if I plug in b here, I get phi of b here, which is d, and this integral becomes this one. Okay? And if I plug in b over here into g, I get the left side. So these two things are equal. Okay? So if I plug in b to both sides here, look at the definitions, I get these two things, as long as I use this fact. Okay? So we just proved U substitution. We proved it using fundamental theorem of calculus. And chain rule, right? Which is, makes sense. Chain rule is just, well, U substitution is chain rule in reverse. Okay? Integration by parts is just product rule in reverse. So let's do that. So let's prove that. This is going to be pretty trivial on this one. So the integral from a to b of u times v prime equals uv evaluated at b minus ua, or uv evaluated at a minus the integral of u prime v. So here, how do we usually write integration by parts? Integral of u dv equals uv minus integral of v du. That's how we usually write it. What this means is u dv means integral of u v prime dx, which is what's here. uv is uv, and then integral of v du means v u prime dx, which is what's here. And then up here, because, well, we haven't talked about indefinite integrals, and we're not going to talk about indefinite integrals. So this is written in terms of indefinite integrals, but the interpretation of that by definite integrals means, well, I plug in endpoints and subtract. So here, plug in b and a on the endpoints of the integrals, and then here, there's no integral here, but I plug in b and a and subtract. So, so this is how we're going to do integration by parts. And it's specific for definite integrals, but we can see kind of how it connects to what we're used to for the indefinite integrals. Okay? The proof is let little f be uv prime plus u prime v, let capital F be uv. By product rule, the derivative of capital F is little f, so by the fundamental theorem of calculus, the integral from a to b of little f is capital F of b minus capital F of a. So this is fundamental theorem of calculus part 2. So little f is uv prime plus uv prime. So I just plug in the definition. Oh, I got it backwards. So just plug in the definition of little f here, right? This whole thing is little f uv prime plus u prime v. So there's a lot of space here. Right? But this is just the integral of little f, which is what's here, and it's equal to capital F of b minus capital F of a. So since capital F is uv, capital F of b is u of b, v of b. Capital F of a is u of a, v of a. So this is equal to this. And now all I want to do is split this integral into two integrals. Right, it's a property of integrals that we know about. And now just subtract this part from both sides. So just move this part over here. And it's this part. Right. Trivial, right? This is trivial. It's just product rule in reverse. Right? So there we are establishing two of our most important properties for actually evaluating integrals. We have u substitution and integration by parts.